Okay, let's look at this question which was asked on chemical kinetics. That is chemistry 1010, question B6. The question was rate constants for the first order decomposition of dinitrogen pentoxide. So that is the first weight constant, and the temperature there it's 293 Kelvin, and the second weight constant is that, and the temperature is 302 Kelvin. What is the activation energy for this reaction? So we've been given two rate constants. The first one is 4.75 times 10 to the power negative 4 per second, and the second one is 1.63 times 10 to the power negative 3 per second also. So we can see that that is the first order because it is obeying this equation. Okay, it's obeying these units, so it's first order. That is simply first order reaction, because if we check the units, we plug in that equation, will simply get the per second, even there it will be per second. So, and we've been told it is just first order, so there is no need even to verify. So in this question we need to use the Arrhenius equation. So with Arrhenius equation we can see that the rate constant is given by A multiplied by E to the power negative activation energy over RT. So from Arrhenius equation, K is just rate constant. Okay, K is rate constant, then A is just the frequency factor. A is just the frequency factor. A, you know that A is a Euler's number. E is a Euler's number, and it is equivalent to 2. E, the value for E, 2.718. That is the Euler's number. Then E with a subscript A, that is the activation energy. Simply activation energy. Then R is just the rate constant. I mean the gas constant. And this is the universal gas constant. So we are talking about energy. So the gas constant would be 8.3145. So no need to master it to be given. And also see, that is just the temperature, and this temperature must be in Kelvin. So basically this is what we need to know. So let me get rid of this. Then we will manipulate this formula so that it suits with what we have. So that will stay here. So we can manipulate this formula to say ln K2, it's the same Arrhenius equation, but since we've been given two rate constant, we can say ln 2K K2 over K1 is equal to negative activation energy. If you just apply ln on both sides, natural log on both sides, you would get ln K2 over K1 is equal to negative activation energy over R, then everything multiplied by 1 over T2 minus 1 over T1. So this is the equation we are going to use. Let me just write it on top. So ln K2 over K1 is equal to negative activation energy over R multiplied by 1 over T2. You can say 1 over T1. If you say 1 over T1 over minus 1 over T2, you would get a negative value, but it would cancel with this negative. Okay, so this is the one we're going to use. So we're going to say ln our K1 would be the rate constant for the first one. So the first one, this will be our K1, and that would be our K2. So this is K2, that is K1. So the K2, we'll start with K2, that is 1.63 times 10 to the power negative 3 over K1, it is 4.75 exponent -4 to be equal to negative activation energy over the universal gas constant, which is, this is in relation to energy, so we use 8.3145, then multiplied by 1 over our temperature 2 would be 303 minus our temperature 1, which is equivalent to 293. So what you need to do is just to punch the values. You can say 1.63 times 10 to the power negative 3 divided by 4.75 times 10 to the power negative 4. Then you find the natural log of this value, and it will give you 1.233302049 is equal to, then you can work out this by just saying 1 divided by 303 minus 1 divided by 293. Then you can also say, since this is on the denominator, you say divide by 8.3145. So the answer you would get is 0.0, actually it will be negative, so negative multiplied by negative activation energy, the negative on the activation energy, the value will now be positive. So 0.000013547, and this is by multiplied by activation energy. Then we divide on both sides by this same value, which is 0.000013547, even on this side by 0.000013547. So let's divide 1.23302.049 divided by 0.000133547. Okay, so the value it is giving, you just get rid of this. Okay, so it's giving activation energy to be equal to 9101.97372, and this is energy, so it will be in joules. So you can even round it off. You can round it off to say, or you can basically write this in standard form. So it will be activation energy is equal to, you can shift this point, so it will be 1, 2, 3, 4. Okay, let me just shift it up to 3. So 1, 2, 3. So it will be 91.02.02. This is a point. Then times 10 to the power negative 3 joules. So you can write it in this format. So that's it for this question.